Okay. Hi everyone. Today we're going to give the presentation on closed-loop camera and monitor color correction project. And our advisors are Matt from CMU and Thomas and Kevin from Facebook Reality Lab. We will first introduce the motivation and project outline, then illustrate the current progress for our pipeline, and finally we will show our future plan. Since our project emphasis more on technical aspect, we don't have existing research papers to follow, so we don't include related works here. And the first questions we may want to ask is, why do we care about the color correction? Actually, how to get color correctly is an important question in photography. We hope cameras can capture the true color as what we see in the real world. But in fact, this is very difficult because manufacturers can easily affect how sensors sense color. So in order to obtain an image with correct color, people use color checker as a reference and do color calibration. This makes captured images more vivid and more real. And for this Facebook project, the team is trying to render realistic human avatars that enable people to communicate remotely as if they are face-to-face. And we want to display human avatars accurately with accurate geometry and also with accurate color. But we can notice that there is still a gap between real human skin tones and the avatar. So our goal here is to fill this gap by the color correction. But doing color correction is quite challenging in this case, since we're not dealing with a single image. We use a multi-camera system like this image shows. And the data set contains images captured by different cameras on different days. We call images captured at the same time as one session. The problem is those images are captured with varying camera properties like lens tap, focal length, and sensor temperature. This will make color inconsistent across cameras. Also, multi-session capturing will cause view-dependent effect. It means that if we put an object in front of the camera in session 1 and turn it to another angle and captured by the same camera in session 2, we may observe different colors because the object will reflect different light to the camera. However, we expect the color to be consistent since human skin tones should remain the same despite what camera I use or when I capture the image. The color is just that color. Therefore, it's very important to explore how to do color correction in this more complicated system. Here is our formulation for color correction across cameras and sessions. Our goal is to learn mapping from the camera ID and session number to color transform. And the color transform should be able to transform the image into a perceptually reasonable color space. We hope for the color value captured by different sensors from different viewpoints. After the color transformation, the color value should be identical. And then I will talk about our project outline. Originally, we're offered 2 directions for the project: learn color calibration across capture sessions and camera and monitor calibration. We decided to choose the first one as our focus, so that's why the project content is not exactly consistent to the title. And to learn the color transform, color checker is used as an important reference. So it's necessary for us to develop an automatic and accurate way to do the color checker detection, mainly because first, we have huge amount of color checker data. It would be infeasible for us to click color patches by hand like what most softwares do. And second, inaccurate inaccurate localization will give us inaccurate input color, so we may calculate incorrect color transformation function. So as the first step, we want to develop a system to automatically detect color checker in images. Then we do the color correction in multi-view and multi-session setting. And next, I will discuss these two steps in detail. The first part it is the color checker detection, which I just mentioned. And existed color checker detection methods are based on traditional image processing approach. The general idea is that we want to first find as many quadrilaterals as possible and then do the registration with color similarity. But this approach requires lots of heuristics and are not robust enough. So we want to find an easier and better approach. And here we treat all corner points as key points and use a key point detector to find those color patches. So here comes to one question: why we use key point detection? Of course, we can also view the color checker detection problem as a segmentation problem to segment all color patches. But why we prefer color point detection here? So mainly because three reasons. The first one is feasibility, which means because pose estimation is already a very successful method in many complicated things, and color checker is a much simpler case. So we are confident that it can eventually work here. And second, in our data set, most of the color checker are occluded. Key point detector can also give us a reasonable result in this case. And also, since we are doing the detection in multi-view setting, we can use some optimization methods such as triangulation to further refine the prediction if we use the key point detection. And for the detection part, we want to first train a robust key point detector and then do the refinement. So what's the major bottleneck here? For the facial, hand, and body pose estimation, they have paired training data, but we don't have such data for color checker. So our solution is to generate a synthetic data set. We create mesh and texture of the color checker and then randomly place camera in 3D space and project color checker to 2D image. Key points positions can be obtained by the projection, so we can generate the paired data. And also we add more factors to make the rendering process more realistic, such as different viewpoints, random background, and we add random noise, color jitter, and Gaussian blur, etc. But when we train and test the network, we found that the network is easily overfitting and just returns some random results during the test time. So what's the problem here? We can notice that even though we do some augmentation, there is still a huge texture gap between the synthetic data and the real data. Also, for the synthetic color checker, all pixels in one patch have the same color, which is very unreasonable in real world. So we propose to first do a global color transform, which multiply each RGB channel with a random scalar. The intuition here is that we want the network to focus on relative color values instead of absolute value. Also, we capture real texture to replace the synthetic one. And here to match the color checker key points on the real texture to key points on the mesh, we need to know the key point positions on the texture image. But don't worry, we don't need to measure them by hand. We only need to manually click for corner points, and then we can estimate corner candidates, and the Harris corner detector will complete the rectification process. And we'll then use Harris corner detector again and apply line fitting to obtain a more accurate warping. These are some examples of the texture maps. And after this step, we finally found that our model can work on the test dataset. Even if we zoom in, we can still notice very reasonable results. And the visualized points here have reference color of each patch. Of course, there are also some failure cases. We found that this is mainly due to some occlusion. So in this example, you can see that the left border without hand occlusion still has some reasonable prediction, but on the right side, the finger is occluding the border, and the prediction of key points near that region is inaccurate. And this suggests that the network still overfits to some undesired areas, such as border is always black and straight. So we use the superpixel to generate some random shape from background image and place them on image to perform the occlusion. Also, we apply elastic deformation to the color checker because the color checker may not be a strict plane in the real world. Finally, we do some qualitative analysis of augmentation to figure out which augmentation method is more helpful for us. And the training and validation set are generated with different background and textures. Here are the numbers. We found that we achieve lowest error when doing full augmentation with real texture. And doing occlusion augmentation and using real textures can improve our result a lot. And then Zhichao will go through the following parts.
Well, thanks, Shuang. Now we have got a robust key point detector, but we cannot guarantee that we can always get 100% precision or recall. So that's why we need the refinement stage. For the single view setting, we can treat the refinement as solving a PNP problem with RANSAC. We can assume the color checker is a perfect 3D plan in the 3D space. And this gives us a set of 3D to 2D correspondences, so we can estimate the viewing angle of your camera and reproject all the 3D key points back to the 2D image plan. So we can further refine the predictions. So here is our final single view detection results for images in the wired. You can see it works really well for different rotations, for occlusions, and for different viewpoints. And we also tested on the different illumination cases. Note that here we are just doing the frame by frame prediction without any interframe tracking knowledge here. You can see even if you place your hand in front of the color checker, the occlusion is not a very severe case. The detection model can still give you reasonable predictions. As for the triangulation, as for the multiple view setting, which might be more interesting for a Facebook perspective, we have got well-calibrated camera extrinsics for the other images. So we can just do the triangulation to aggregate the predictions from different frames. It shows several advantages compared with the single view PNP baseline. Because when we do the sole PNP in the single view setting, we assume the color checker is a perfect plan, but it's not always the case. So for the outliers, we can see the reprojected key points doesn't align really well with the ground truth, but it's not the case. But it's not an issue for the triangulation because we don't assume it to be a perfect plan. And another advantage is sometimes we will view the color checker from an extreme viewing angle. This will result in a severe distortion for the color checker in the image. For the single view setting, the model cannot give you any reasonable predictions. But thanks to the triangulation, we can borrow the information from other frames and reproject the failure key points into this failure frame. We can see the prediction is still very reasonable. But there is still a small chance that the triangulation might fail. Here are some examples. It is mainly due to the failure of triangulation. For instance, the key point is only visible in a single camera, so we can do not do the triangulation. Or other visible points are treated as unconfident predictions. But luckily, we have got more than 95% correct predictions. So this can be easily addressed by using some local geometrical rectification. We can just slide a window within the color checker and approximate all the points within each window as a plane and solve a local PNP problem within it. Then we can do the rectification. So here is our final multiple view key point detection results. We can find it works really well, even for some very challenging viewpoint cases. If we zoom in, we can find it almost aligns perfectly with the ground truth. So to summarize, we find a key point detector is really effective for color checker detection. It's necessary because we want to automate this process for large quantities of data sets across different cameras and different sessions. And the precision is crucial for the accurate color value sampling from the color checker. And we found the realistic synthetic data set generation is sufficient to train a robust model. And we need several augmentations to make the final model work. For further refinement, we can solve a PNP problem for the single view setting and perform triangulation for the multiple camera setting. Now let's move to the next step of color correction. Here we call it typical color correction because we treat this as a baseline and it's a standard practice. And let's recall the formulation of our color correction across different cameras and sessions. Our goal is to learn a mapping from the camera ID and the session number to a color transform. Here we make two assumptions to simplify the problem. First, we assume the mapping is independent of the session number. That is, the color transform is a property of the camera. It is fixed for the same camera across different sessions. The second assumption is the color transform is parameterized with an affine transformation matrix. So here is the pipeline of our current standard color correction. At training time, we just use the color key point detector to assist the sampling of the color checker values, and then we solve our color transformation matrix with respect to the reference color. Then at test time, we can apply the transformation matrix for arbitrary sensor image and get the image with the correct color. For more details, for every given camera, we have an image capturing a color checker. So we can run a key point detector array it. Then we sample the color values within each patch and average them. This gives us our sampled color value vector. It's of dimension n by 3. Here n is the number of different patches in the color checker. Then we solve a least square problem. That is the transformation matrix by the sampled color space. Sampled color value space should be similar to the reference color space. As we can see here, we just treat the estimation of different cameras independently. And as we just mentioned, our motivation is to make sure that different cameras, when they view the same 3D point in the physical world, their sensed color value should have identical values. So here we can introduce an additional consistency term. That is just another L2 distance between the transformed color space for every pair of the different cameras. Here, lambda is a weighting to balance the importance of the different terms. At the test time, we have an input sensor image, and we have the corresponding transformation matrix already estimated. So we can apply it to get the affine transformed image. But both of these are still in the linear color space. To display it correctly in our monitor, we do the gamma encoding. So we got the conceptually very reasonable correct image on the right. But it's in the non-linear color space. As expected, the current pipeline might have some limitations. An obvious effect is the illumination. We do some visualization here to illustrate this problem. In the middle figure, we can see the white patches in the top row and the white patches in the bottom row. And when we zoom in, we place a small square with the ground truth color in it to show the contrast with the transformed color and the ground truth color. We can see the white patches in the top row and the white patches in the bottom row. They have different levels of the contrast when they compared with the ground truth color. This is due to the non-uniform illumination distribution across the color checker. This indicates that the current transformation procedure maps the different patches of the same color to different values. That's definitely undesirable. So we can add an additional lighting adjustment step before the color correction. We can assume that the intensities of the white patches change linearly with respect to the illumination change across the color checker. Then we can interpret a function f such that the f times the intensity of each pixels in the white patches, they equal to some constant value. Once we have the interpreted function, we apply it to every pixels in the color checker. So we got the lighting adjusted sensor image on the right. So here is our result after the lighting adjustment step. And this time we can see the white patches in the top row and the bottom row, they possess the same level of contrast compared with the reference color space. And numerically, we get lower error. Here is the test results on the human images. Every time for every camera, we just estimate a transformation matrix and apply it to the across different sessions, but for the same camera. From the left to right, we get the sensor image in the linear color space, the sensor image with gamma encoding, and the correct image still in the linear color space. And finally, we get the correct image after the gamma encoding. So comparing the second and the first column, we can see it's necessary to do the color correction. Your camera sample cannot always give you the real color. Here is more results for different cameras. And we also experiment with the consistency issue that we just mentioned. Here we show our 4 examples. They are all estimated independently with respect to the without considering the mutual consistency. That is, we only optimize the loss with the first term and set the lambda as 0 here. We can see all of them are perceptually reasonable. They achieve low error with respect to the reference color space. But when we compare them across different cameras, we can see the color value actually is not consistent. But after introducing our consistency loss term, we can see they are still perceptually reasonable. And for the same 3D point in the physical world, when we view it from different cameras, we can see the sensor value have better consistency here. So to summarize, solving a least square affine transformation can give us a reasonable absolute correction with respect to your reference color space, but it only works for the single camera and single session setting. Though we can introduce an additional consistency loss term that can improve the consistency across different cameras and sessions, but currently we parameterize the transformation matrix with an affine transformation, and we do not consider the view-dependent effects. And another problem is the affine transformation might not be expressive enough. So here is our future plan. First, we plan to open source the color checker detector to the community. And we hope to explore more expressive representation for the color transformation, maybe using an MLP. And finally, we would like to take the concept of black level, saturation, and noise into consideration, and even use the knowledge of the sensors. Yeah, that's all. Any questions?
Great. Yeah, thank you very much. So let's start with questions from the faculty reviewers that are here. So we have for this talk, well, Matt is here, Yannis, Christoph. Yeah. So let's start with questions, and then if we have time after that, we can open it up to the rest.
Yeah, I have a question. So what is your goal? I mean, does it have to be just pleasing to the human eye, or do you have some numerical value that you need, or a quality measure that you have to achieve?
I think just for the standard practice, it can already give us very perceptually reasonable predictions for different cameras, different sessions. Our goal here is to achieve some numerical consistency between different cameras and different sessions. Because when Facebook is doing their after training, they need to leverage the training data from the images captured with different cameras and different sessions. You want to optimize the image similarity. But if they are numerically unstable, I mean, this is where this can be problematic in terms of the final optimization.
Hey guys, I have a quick question here. So, I mean, I realize that this is looking perhaps forward to the next semester, but I'm curious how things are going to change when you start taking into consideration the displays that you're using to visualize these results. Like how you see this moving forward in terms of taking advantage of or making use of the, for example, the gamma functions associated with different displays. How are you going to tackle that problem?
I think this is still an open problem, and we're also discussing this with Thomas from Facebook, and obvious, we can see some obvious limitations for the current method. I mean, we just use a transformation matrix independently for every cameras, and it's just a lookup table. And I mean, the input to the lookup table is just the camera ID, and we do not consider the session number. I mean, for the same camera, when the viewing angle changes, the color transform also changes, but we do not consider that effect. So, contrary with but I think this is just a personal idea. I think yes, maybe we can consider some more representative or more expressive representation of the color transform, such as an MLP, and maybe we can use a neural network, take a single image as input, and try to predict the net weights of your MLP. Then we can, so the input of the network is a single image, and the output is the weights of the MLP. So it can take into account more factors, including the viewing factors. And then when we do the color transformation, we just feed the color values into the MLP and output the transformed color values. So it gives you more expressive power, and we also take into account more factors.
I guess just to perhaps build off of that. So the original title is Closed Loop Camera and Monitor. And I realized that, you know, so far you've covered basically the camera aspect of things. I'm wondering how you're going to close the loop.
Actually, this is another. Actually, we have originally we have two options for our project. Closed loop monitor and camera calibration is one of them. But now here we decided to do another project. It focuses more about the consistency between the color correction for different cameras and different sessions. So here we do not have the concept of a monitor here, I guess.
Okay.
Yeah, we just want to achieve the identical sensor values.
Yeah, so I had the same question as Matt about displays, but that's already been answered. I also had a couple more other questions. One is for the detection. Of the color checker. Can you actually use the fact that you know what the appearance of this color checker is to improve your detector? Basically that, you know, wherever I find these corners, if I go and normalize with respect to one of the corner patches, I expect all of the intensities to look like a specific set of values.
Yeah, I think that that makes sense. And but so here, I think we're just trying experimenting with the most powerful method, most feasible points to solve it. I just want to make our life easier. We just treat it as a key point detection.
It's actually
we do not consider the relationships between different key points.
It's just something that is very structured. You know, both its geometry, but also its appearance is very structured. It seems like a waste of a very useful constraint to not take that into account in your neural network.
Yeah. I think that makes sense. And here, I think But from our current experiment, we find even if we do not consider that, the result is already pretty good. We just use an off-the-shelf key point detector for human pose or hand pose estimation and apply it here. And we find it works surprisingly well. We think the